I'm Harshni Bhupati, Executive Member of IIChE Students Chapter Shastra. Now, on behalf of Students' Council, I welcome our chief guest, Dr. Mahesh Nagargoje, Project Research Scientist, IIT Madras, Dr. P.R. Naren, Associate Professor of Shastra Deemed University, a beloved alumni and student Talk of the Month. A short note on Talk of the Month. The Talk of the Month is a virtual talk series given by external experts from industry and academia on chemical engineering. The virtual talk series acts as a shared platform for the current students and for the graduates of Shastra to interact and gain knowledge from the invited speakers. And it is conducted on weekends so that our alumni can also participate. We are resuming this after a while, and this is our fourth virtual talk in the series. Now, I request Mr. Sashank Raman, Chairperson of IIChE Students Chapter, to give a brief introduction about our chief guest. Sashank, please take over.
Thank you, Harshini. Dr. Mahesh Nagargoje is a distinguished expert in the field of computational fluid dynamics and has made significant contributions to this field, particularly in the study of fluid flow in biological systems. Dr. Mahesh completed his undergraduate studies at Shivaji University and obtained his master's in chemical engineering from Dr. Baba Saheb Ambedkar Technological University. He later pursued his PhD from IIT Guwahati, where he conducted research on physics of single and two-phase flow in bifurcating vessels under the guidance of Dr. Raghavendra Gupta. During his doctoral studies, he worked on CFD modeling on patient-specific cerebral aneurysms to predict initiation and rupture risks, which has important implications for the treatment of this condition. Dr. Mahesh is an accomplished researcher and has published numerous articles on his research in top-tier journals such as International Journal of Multiphase Flow, Physics of Fluids, and Computational Methods in Biomedical and Biomechanics Engineering. He has also presented his work at various conferences and workshops, demonstrating his commitment to share knowledge and collaborating with others in this field. In recognition of his outstanding achievements, Dr. Mahesh has been awarded the prestigious Marie Curie Postdoctoral Fellowship and will be continuing his research on stroke treatment in Italy. We are honored to have him here today with us and looking forward to learn more on this groundbreaking research. Thank you, Dr. Mahesh Nagargoje, for coming here, sir.
Thanks, Shashank, for this introduction.
Thank you, Sashank. Now, I request our chief guest, Dr. Mahesh, to deliver his talk. Sir, please.
Yeah, thanks, Harshini. Thanks.
Welcome, sir.
I'm sharing my screen. Is it okay? So my screen is visible.
Yes, sir. Yes, sir.
Okay. So good evening, everyone. Thanks for inviting me to Shastra's IIChE student chapter. So I will be presenting today's title will be patient-specific cardiovascular modeling, an affair between medicine and engineering. So for the short, I would like to say that it's a interdisciplinary approach. If you are dealing with the biomedical simulations, it's an interdisciplinary approach. Specifically, you need to have knowledge between medicine, at least anatomy and physiology, and then engineering. So I will explain how we can go for such how to achieve such research career. So currently I'm working as a project research scientist at IIT Madras, but it's a collaborative project between Department of Neurosurgery, Sri Chitra, and IIT Madras. And I will be joining in a short as a MSc postdoctoral fellow in Polimi, Italy. So what is the interdisciplinary approach? So I would start with the parallelly. So first medicine and second the engineering. So when I go to top-down approach, then in medicine, we should have knowledge about the physiology. In engineering, fluid mechanics. Then in physiology, we should know blood flow patterns, various cardiovascular networks. And that can be solved using CFD. So we should have knowledge about CFD. I'm I hope that everyone knows about CFD. It's, I think, undergraduate course, computational fluid dynamics. Then what we can gain from blood flow patterns, that is atherosclerosis. It is a name of disease. This is a medical term, but in layman language, I can say stenosis formation or fat accumulation in the arterial wall, which reduces the cross-sectional area available to flow. That we called as a atherosclerosis. And that can be correlated or predicted using our CFD simulations. That is, main parameter is the wall shear stress value, and it is very well accepted in the medicine community that wall shear stress or the lower wall shear stress region is the probable region for formation of this cardiovascular diseases. When we have both like this all the information, or I can say knowledge, then we can go for personalized medical treatment using in silico approach. In silico is kind of computer simulations. We use computer simulations, for example, directing the surgeries or making the personalized stent designs, or heart walls. That can be done if we are familiar with these both branches in a depth. Then motivation. So before going for the various results, I would like to give some background information about this area. So this is, we can see this is a cardiovascular system. Central part is the human heart, which pumps blood throughout the cardiovascular network, and that can be, we can see the blue color is a deoxygenated blood which is coming to heart, and the red one is the oxygenated blood which is supplied to various body organs, and that is supplied by, this is the we can see this image or video, that is the human heart, which is consist of four parts. The right atrium, just I can divide it into atrium and ventricle. Atrium is top part, ventricle is bottom. So atrium, right ventricle collects the blood, it supply, then ventricle pump it to lungs, then oxygenated come into the left atrium, and from left ventricle, it from the aortic arch, it will supply to all body or various organs. Then today I will focus on majorly focus on the cerebrovascular flows, which means that blood flow to upper body parts, that is brain. And this is the image we can see. This is the video which shows that how it occurs. The stenosis occurrence observed at bifurcating regions. How and why it is happening, that I will discuss in further slides. So this is the typical MRI image or CT scan image, I can say, how it will differentiate inner and outer wall. Here, just I want to notice that this is the outer wall, these regions, which is having higher thickness as compared to inner. And this has been found in a lot of studies. And this is the carotid artery bifurcation, which is the major artery which supplies blood to brain. So why to study or why to focus on this area? As we know, cardiovascular diseases are the leading cause of death globally, taking an estimated 17.9 million lives each year. And in India, this number is very high as compared to other countries. Most of the India, we called it as a cardiovascular diseases capital, I can say, like the diabetes only, because here every day we are nowadays seeing very young people are dying because of heart and these cardiovascular diseases. So in my PhD, I have a very big challenge to how to start with this area. Being chemical engineer, I have to start from scratch. So I know that this area, a lot of researchers have done, I can say a lot of research articles you will see, but I have to give some fresh perspective to that research. So when I was doing literature, I found that most of the researchers done this. Suppose this is the carotid artery, there is a bifurcation angle. They have considered it as a symmetric, which means that the both angle between these both vessels are symmetric between both daughter vessels. But in cardiovascular network, it is not true. There might be asymmetry, and it should be, because it is very complex and big cardiovascular network. So I have picked that, how asymmetry will affect. Secondly, there is a sinus. I can say this is dilated region that we called as a carotid sinus, and that is also unique in each patient, each human being. So we have to consider those regions also. So we try to vary the geometric variation in sinus as well. And then comes into picture the low wall shear stress theory, which was proposed by Caro et al. In 1972. They proposed that in the regions where the wall shear stress is low, that is the most vulnerable region to development of stenosis or the atherosclerosis. And that is this proposed by Caro in 1972. But till now, medicine community is accepting this theory. So before going for results, I will give some background information about various branches such as physiology, engineering, and imaging techniques, because these three will combine and then we will go for patient specific. So first is the physiology. This is the, I can say, Galen. He was like godfather to modern medicine. So, but problem with that, he proposed that blood production takes place in a liver. According to his experiment and experience, he proposed this hypothesis, and he said that blood circulates from liver to all over the body. Then everyone knows Leonardo da Vinci. He's a great scientist. Also, he was a very good painter. Also, so what he did, the human anatomy sketches he has drawn in 15th century, and it got published in 19th century. So he drawn almost 240 individual drawings of human anatomy. And even today's world also, most of the physicians use his drawing for teaching purpose or understanding the anatomy. Then there are a lot of researchers, but I am just focusing very selected, or when there is a large change in the research. So from Galen to 129 AD to 15th century, people were believing that blood production takes place in liver, which was not true, and complete research was directed or peripheral around these findings only. But William Harvey dared to prove that these assumptions was wrong, and he first time found that blood flows around the body and pumped by heart in a closed loop. Then the I can say the contribution to fluid mechanics, how fluid mechanics develop over the years. So we know that Sir Isaac Newton, he has proposed the Newton's law of motion, and we know second law of motion, force is equal to mass into acceleration. Then comes into picture the Bernoulli. He proposed the relation between pressure and acceleration. There is an inverse relation. And then Euler extended this, and he put this relation into the this second law of motion, and which we called in fluid mechanics, which we called as Euler equation, which is a ideal Navier-Stokes equation for in-viscid flow. But problem with this Euler's equation was we are not considering the viscous forces. We are dealing with only ideal fluid, which is not having any viscosity. But such fluids are not exist in the actual nature. So we have to add viscous term also, and that has been done by Navier. He added the viscous term to this equation, and Stokes derived this equation and gives us the Navier-Stokes equation. Even today's world, we are using same equation for solving all problems, cardiovascular fluid in biomedical flows, as well as aerospace, as well as chemical industry. In all process industry, we use this to solve the fluid flow or predicting the fluid flow. But after deriving this equation, problem was that till now we don't have solution for this, analytical solution for this equation, because if I solve for Cartesian coordinates, we will get 4 variables and only 3 equations, which is impossible to solve. Then the technique called CFD comes into picture. What CFD does, it will assume the pressure terms, solve the velocity component, put that velocity in continuity, because we know continuity equation del U is equal to 0. So after putting into it, we solve iteratively in such a way that we are satisfying this continuity boundary condition, and then we get the velocity and pressure terms, and this is the typical flow for the CFD. Then imaging studies, medical imaging in a short I can say. So first the W.C. Röntgen, he invented X-ray. He was not intent to invent the X-ray. He was doing some cathode ray tube experiments, and he has shield over that cathode ray tube. But he found that some rays are penetrating that shield. Then he was curious to know what exactly it is. And then he found that there are some rays which are propagating or which are penetrating that shield, and he don't know name, so he given X-ray. And even today we use the same term, X-ray. For this invention, he got first Nobel Prize in Physics in 1901. And first image, which is very, I can say, everywhere you will see this figure. This ring you can see, this is the hand of his wife. So first time this is the first image took by X-ray, and you can see this engagement ring and bones. Then this techniques has been used in world wars. It was very difficult to locate the bullets into the human body, so they have to cut a lot of places, and then they have to remove the bullet. But from X-ray invention, they can detect the exact location of bullet, and just the surgery or cutting, the area of cutting decreases, and loss of blood will reduce because of this technique. And we can see this white bullet, and by detecting such, they used to do surgeries. The next is the CT imaging, computer tomography. It is nothing but an extension to X-ray, but X-ray is in one direction, but in CT we used to have all 360 degree in all way. We have X-rays, and from that we can get whole image of body. And for this invention, he also got Nobel Prize in 1979. Then, but problem with the CT was that it was not clearly differentiating between tissues. For that, MRI comes into picture, magnetic resonance imaging, and that has been invented by Raymond Damadian in 1969. And then improvement in MRI took place by Peter and Paul, and they got shared a Nobel Prize in physiology in 2003. So this is typical improvement in imaging techniques. Then next comes into the patient-based modeling. We have physiology understanding, we have engineering, for example, fluid mechanics understanding, and then imaging techniques. Then patient-based modeling comes into picture, because we use all three into this, because it's a interdisciplinary branch. You can see this. He is a David Steinman, professor in Toronto University. He was he is a very old guy who is working in this field. I think he published his first article in 2002. He is completely dealing with image-based hemodynamics in carotid artery and cerebral aneurysms. Then Charles Taylor, I hope that you know about heart flow. He founded this company. This company gives the CFD simulations to surgeons for directing the surgeries, specifically for heart surgeries. Then Alison Marsden, she is a professor at Stanford University. She developed this software called CMuscular, which is very useful if someone wants to do a career in this patient-based modeling. They can go through it. Patient-based modeling of various arterial models, they have developed it, and it is now open source. Then Professor Alberto, he is also professor at Michigan. Similar to CMuscular, he is having another software that is Crimson. Both does the same thing. It is having from loading the medical images to simulating and post-processing. All you can do in single software. And it is open source, so anyone can use it. Then, as I was discussing, the next is the Ajit Yoganathan. He is having very well-known book, Circulation, which is used for everyone who studies cardiovascular fluid mechanics. He is a very well-known guy in heart wall mechanics and development. He is a chemical engineer by profession, but he works completely in heart wall mechanics. Now I will start with the cerebral blood flow and carotid artery, because this is the largest artery in circulation to brain. So this is the aorta. From that, there are pair of carotid arteries, two carotid arteries on both sides. There is an external carotid artery which supplies blood to face. Another one is the internal carotid artery, which is having sinus that goes into the actual brain part. And at brain, we see that there is a closed loop formation, which we called as a circle of Willis, which was invented by Willis. That's why his name has given to this region, circle of Willis. If I focus to carotid artery, it is having two, internal and external, and then the bulb dilated region, which we called as a sinus. And we can see in the video how the stenosis occurrence in the carotid artery. because of the complex flow, which I will discuss in rest of the slides. The major part why we study the cerebral blood flow dynamics. The 15% of the cardiac output goes to the brain, but the weight of the brain is only 2% of body. So I'm trying to say that for such a very small mass, it is here, brain requires a lot of blood, that is oxygen, and that's why it is a very important part. And second, it operates or all body movement or all the actions. That's why blood flow to the brain is important. And what happens to if there is a cut or there is a delay in blood supply, or there is a no blood supply to brain, what will happen? That I will discuss. Then first, as I discussed earlier also, effect of bifurcation angle. So you can see that there is a top figure which is a both are carotid artery, top and bottom. In top figure you can see that bifurcation angle is small and it is kind of symmetric between both daughter vessels. And the bottom one, you can see the internal carotid artery, which is having sinus. This is very the bifurcation angle is very large. And this study has been published in 2019. They have done for 150 patients, and they found that those patients which are having large bifurcation angle, they are suffering from stroke. So we have decided to explore this, and then we try to do the pulsatile blood flow dynamics in symmetric and asymmetric bifurcating vessels by comparing Newtonian as well as non-Newtonian fluid. If someone wants to explore more, they can go through these two papers which we have published on this bifurcation angle effect. So for starting, it is very difficult to have patient-specific images and with such a varying bifurcation angle. So we started with simple geometry because we have control over this geometric variation. We have used this ideal geometry. This is inlet waveform we have implemented here, systole and the diastole. General cardiac cycle will consist of systole and diastole. Then various cases, symmetric and asymmetric. Symmetric means alpha and beta angle are same. Asymmetric means there is a difference between two. And we have selected these 6 cases that we have simulated. And then Newtonian and non-Newtonian, we have used carry-medal. These are the various parameters which we used. And how viscosity varies for non-Newtonian, we can see that with increasing shear rate, viscosity is decreases because blood is a shear thinning fluid. And we go for the simple what is the velocity distribution at the bifurcation, and we can see that at bifurcation there is a skewed velocity profile, which means that at inner wall velocity is very high, which means that at inner wall shear stress will be higher, and outer wall you can see here there is a recirculation. I will just pointer option. Okay, then outer wall you can see there is a blue color which shows that very low velocity or there is a recirculation. When we compare Newtonian and non-Newtonian, we see that Newtonian having 4 vortices. These are the Dean vortices, which occurs due to curvature effect. There is a due to curvature, there is a pressure imbalance at the both edges, which creates the secondary flow. And we can see that in Newtonian it is very high as compared to non-Newtonian. Second observation is that in Newtonian case we can see maximum velocity is slightly higher than non-Newtonian. Then what happens to these velocity profiles in a cardiac cycle? In peak systole, we can see that there is a the skewed velocity profile, but there is a no skewness, very high skewness in the velocity profile. But when you go to beginning of diastole, we can see that the velocity profile is very parabolic at the inner wall, and at the outer wall, the recirculations are very high as compared to other locations. Even at end of diastole, we see that the recirculations are less, which means that at the deceleration phase or at the end of systole or beginning of diastole, the recirculations are more. And at the end of diastole, we can see there is a difference between Newtonian and non-Newtonian, very noticeable difference, which is absent in other cases because of here the shear rate is very low. That's why due to shear thinning behavior, it shows different in velocity profile, difference in velocity profile. Then we have plotted the vorticity. How the flow vorticity is nothing but a curl of a velocity vector. It gives the strength of the rotation, and we can see that here there are two counter rotating vortices, as I discussed in previous slide also. But what is difference between Newtonian and non-Newtonian? We can see that in Newtonian, strength is very high as compared to non-Newtonian. And second, when we increase the angle, we can see here at the fourth location, we can see the strength is very low. Almost it is diminishing at the fifth cross section. But in higher angle, it is still there, which means that at higher angle, the vorticity is very high, and it, it is not diminishing even at outlet. Same happens with the helicity. Helicity is nothing but just multiply to vorticity by velocity, which gives the helical motion, and how that helical motion is in bifurcation angle. The trend is similar like vorticity in helicity case also. Then quantitative comparison is also important, and specifically wall shear stress values, time average wall shear stress that we have plotted in outer and inner wall. So we can see that at inner wall, the velocity, time average wall shear stress is very high at this junction carina because of that skewed velocity profile. But at outer wall, this is very low. But when we goes to downstream, we can see that the higher bifurcation angle, this blue color, is having low wall shear stress here because of recirculations. And when we compare with Newtonian and non-Newtonian, we can see dashed line is non-Newtonian, which is having higher time average wall shear stress as compared to a Newtonian case. Second observation is that when we goes from when we are increasing angle from 30 to 60, which means that this angle we are increasing, then we can see that the maximum value of time average wall shear stress is reducing. Here it was almost 7, and in this case it is 4.5 to 5. Till now I was discussing with symmetric bifurcation angle, but what happens to the asymmetric case? This is the asymmetric lower angle. This alpha is having low bifurcation angle and beta is having high. And from velocity vectors itself, we can say that there is a large flow fraction goes into the lower angle vessel as compared to the larger angle. Velocity is also large. But interesting results we found that in case of symmetric, this flow distribution between both vessels during cardiac cycle was equal. But when we go for asymmetric case, we found that the flow fraction is changing within a cardiac cycle. And specifically when we have this beta upon alpha, which means that the angle, larger angle is very high as compared to lower. In that case, the flow fraction is very low, almost it touches 0 in some cases, which means that in larger angle, at the peak systole, blood is not going into the larger angle. Maybe that is the cause for this stroke, because in this case also we found that angle is very large, and maybe in systole there is a disruption in the blood supply to brain. As like earlier only, I am showing the vorticity, but here there is asymmetry, and we can see that lower vessel is having very high vorticity as compared to the larger angle vessel. And again, Newtonian non-Newtonian comparison, Newtonian is having very high. When by increase, this is the alpha 1560, very high angle as compared to the lower one, this beta angle. Here 4560, then we can see that there is a very minute difference between the vorticity in both daughter vessels. But here there is a significant difference because of high beta upon alpha angle ratio. Similar trend for helicity, like the vorticity in asymmetric case. Again, the quantitative comparison, the behavior is similar. When we increase from this A to C case, total bifurcation angle is increasing. That's why the value is decreasing. But here also we found that there is a difference between Newtonian and non-Newtonian. Specifically, this non-Newtonian is a larger time average wall shear stress. In all the results, I'm trying to say that when we are having very low wall shear stress values, those are the regions which are vulnerable to formation of stenosis. And these are the region which in this case, larger angle are the regions which is having probability of stenosis. Till now I was discussing about the bifurcation angle. So next I will discuss about the carotid sinus. Sinus, this is the ideal carotid artery bifurcation. This is the sinus, we can see dilated region. But in each person, the geometry is different in each case, each human being. The size will be different, this location will be different. That we have varied, and we try to get some inputs into the flow dynamics. And in this case, we are changing. A case, the sinus region is away from the bifurcation, and C case, it is very close to bifurcation. But when it is away from bifurcation, the recirculations are much higher, and that can be confirmed from this secondary flow streamlines, which is superimposed on x velocity. And in this case, A case, when there is a away from the when sinus is away from bifurcation, we see large recirculations, which means that when we are having large recirculation, which means that those regions are having low wall shear stress. Second, when I am increasing the size of the sinus from A to C, A smaller size, C case it is very large. In A case, this is outer wall. Recirculation is present in the outer wall. But when I'm increasing the sinus size, we can see there are recirculation on both the cases, inside inner wall as well as outer wall of bifurcation. And this is confirmed by the similar contours of velocity magnitude. C case, we can see that on both sides there is a very large region of dark blue color, which is recirculation, and which reduces the wall shear stress. And I can say these are the regions, if I having sinus away from the bifurcation and the larger sinus, those are most that is having more higher probability of stenosis formation. If someone wants to explore more or read on this more, they can go through this article, computer methods and programs in biomedicine, which we have published on this research work. Then quantitative comparison, we have plotted the lines on inner and outer wall, and we tried to get some quantitative values of wall shear stress. And we found that this is inner wall, which is having maximum velocity, wall shear stress is very low as compared to the inner wall, along the inner wall. Outer wall is having low because of recirculation. Second, when we increase the sinus size from 8 to 12 mm, in 12 mm case, larger sinus, the wall shear stress value is very low as compared to other cases. This is for both inner as well as outer wall, we can see. Then I will discuss about the realistic carotid artery bifurcation. Till now, I was dealing with only ideal cases. Now I will switch to realistic carotid artery bifurcation. Here we will vary the pulse rate. I will show. So typical, I will first show only typical flow patterns in realistic carotid artery. This is the streamlines, and we can see that in sinus, the recirculations are very high as compared to other cases. That can be confirmed by this velocity contours. We can see dark blue color in the sinus, which shows recirculation. And in wall shear stress, this video wall shear stress, in this case also, this shows variation during cardiac cycle by changing. And we can say that throughout the cardiac cycle, we are seeing very low wall shear stress in sinus, which means that this is the probable reason of the formation of stenosis. So in this case, we have objective of changing the pulse rate, which means that we used to say that do the cardio exercise. It will reduce your cardiovascular diseases. And we try to explore that only. So that's why we have changed the pulse rate, decreases pulse rate. And we found that when we are decreasing pulse rate, which means that our heart is in rest condition. In that case, recirculations are more. In A case, we are having very high pulse rate, which means that we are doing exercise, and then only we are having high pulse rate. And in that case, the recirculation are more, which means that the deposition of fat, chances of deposition of fat is less in case of cardio exercises. That is confirmed using these streamlines. Then another very hemodynamic parameter is the time average wall shear stress. And we can see that when we are decreasing the pulse rate, the low, the blue color region of blue color is increases, which means that low time average wall shear stress region is increasing, and which is the indicative sign for stenosis formation. Next is the relative residence time. In layman language, I can say that this is giving the indication of how much that fluid spending time on that region. So This red color is showing those regions which is at those regions fluid is spending much higher time. And when such things is happening, that is also called as a stagnation, which is the indication of formation of stenosis. And when we are having low pulse rate, we can see this region is high. But when we are increasing the pulse rate, doing the exercise, this region is reducing. So till now I was discussing about the CFD, but there is another research area I can say, that is the particle image velocimetry, because most of the surgeons or medical practitioner, they will not believe in CFD results. They need some validation, and that can be done by using these experimental techniques, particle image velocimetry. So here, what we have done, we have collected that image, CT or MRI image, convert that into STL file using various softwares. There is 3D slicer, Mimics, or Simvascular. Then export it to 3D printer. This we have printed in IIT Guwahati, 3D printed the carotid artery, realistic carotid artery. And this one we have printed from, there is a startup called Trandom 3D China. They just, we have to give them STL file, they will give us these models by printing. And this is the silicon model with flexible walls. So we have used this silicon model for our PIV studies. First, we have to do refractive index matching to avoid the disturbance at the interface to get the proper images or accurate images. And in PIV, we have four various sections. First is your fluid flow, which is flowing through particular object. Second is the laser. In fluid flow, we are seeding some particles. When we put laser, that particles will get illuminate. We can see this green color, that is the illuminated particle. And from camera, we can capture those images at very short interval of time. Then we have two images and particle locations. Then we can compare, or we call it as a cross correlation. From that, we will get velocity vector, because I have time, I have the movement, that is distance. From that, I can calculate velocity vector. And this is very useful technique because it gives velocity vector throughout your domain. Then how refractive index matching we can do. So for example, this is carotid artery. We are supplying air. There is a distortions. So when we use water, slightly improvement. But when we use blood mimicking fluid, which is having glycerol, water, and Na salt, which is having similar viscosity to blood, and we can see that here that refractive index matching is done, because we cannot differentiate between this checkered board and the edges of the carotid artery. After that, we have started the PIV. We have done PIV experiment, and this is the raw image of seeding particles we can see. And at the inner wall, the flow is going unidirectional, going in the downstream. But at outlet, we can see there is a recirculations, and which we have confirmed using experimental technique. This is the post-process image. We can see there is a recirculations here, and this is CFD results. So till now, I was discussing about the carotid artery. Now I will switch to more specific disease, that is cerebral diseases. We have stroke, but stroke is having two types. One is hemorrhagic stroke, another is acute ischemic. So what happens in hemorrhagic? The blood vessel will thins, and outpouching of blood vessels happens like this, and it will burst. After bursting, you will see blooding in the brain, which creates very dangerous situation. Sometimes the patients will die, or in golden hours, within 2 hours, we have to the patient has to reach to hospital for saving his life. Second is the acute ischemic stroke. In this case, in hemorrhagic stroke, the blood vessel will rupture by dilation, and in acute ischemic, there is a clot formation in the artery, and that will reduce the blood supply, or that will shut up the blood supply to brain, and which creates problem because there is a deficiency in the oxygen, and the cell starts to die, brain cells. So first I will discuss about the cerebral aneurysm. Hemorrhagic stroke is a broad term, but that is happening due to these aneurysms. That aneurysm is called as this is suppose brain vessel, and there is a dilation that we called as a aneurysm. Hemorrhage, before happening hemorrhage, there is a dilation which we called as a aneurysm, that I will discuss what we have done. So recently we have published influence of morphological parameters on hemodynamics in internal carotid artery cerebral aneurysms. We have published in Physics of Fluid. It was selected as a featured article, and also we got some media attentions. We can see Science Daily, The Hindu. We got some APS. They have written blogs and some news articles. So first I will discuss about the anatomy of the brain. So this is the circle of Willis. I will not go into details. Just I can say that from carotid artery, I was discussing that there is a external and internal. So that internal carotid artery comes into the actual brain here to ICA. That goes to middle brain, anterior brain, and posterior. Anterior means front side, posterior means back side. And there is a closed loop formation which we called as a circle of Willis. And we can see that, or medical imaging also research about this, and they found that there is a very high chances of formation of aneurysms in this circle of Willis only. So that's why, and this aneurysms having two types. One is fusiform, which is having symmetric geometry dilation. Another is having saccular aneurysm. It will like balloon type outpoaching in one side only. And how flow dynamics happens in this side wall aneurysm, because brain generally this side wall aneurysm is we will generally see, and this is happening in aortic aneurysm in bigger vessel, but in brain we generally see this balloon type saccular aneurysm. In saccular itself, there are two ways. It can happen in curved vessels because of this asymmetric distribution of velocity. Outer wall is having higher velocity that causes this dilation. Second is at the bifurcation carina. I was discussing in ideal case also. At bifurcation, the wall shear stress values was very high. Because of that, also this dilation may occur. But what are the types of this aneurysm formation? How it happens? There are two ways: high wall shear stress as well as low. But in high wall stress, what happens? In high wall shear stress aneurysm, it looks like very small. The reddish in color, we can see left figure of this aneurysm. And in low wall shear stress region, it is like a atherosclerotic aneurysm, which is having these white regions, and that is very large. Two ways of formation of this, low as well as high. And in our case, what we have decided, we wanted to know how flow dynamics changes when this aneurysm is progressing from smaller to larger, because first it will be a smaller aneurysm, then it will increase its size, and after certain enlargement it will rupture. So that we wanted to explore, and here we have changed two parameters, that is aspect ratio and size ratio. Aspect ratio is nothing but the perpendicular distance of this aneurysm divided by its neck thickness, and size ratio is largest length divided by parent vessel. These are the two highly ranked geometric parameters, which is very important in understanding the rupture mechanism that we have considered. This is the typical flow chart from loading the images. We use 3D slicer to create the model. Then we mesh it using ICM, and after performing the simulations, we can get results. So in this case, in CFD, we generally use, we have to do the mesh independence that we have done. And we found that this medium size, by comparing the wall shear stress, we found that this medium size is sufficient mesh, sufficiently resolved mesh. Second is we have to give the patient-specific inlet velocity profiles. So this is we can see this black box, which is having the TCD data, transcranial Doppler. We have get this data from radiology department. They have provided in the internal carotid artery region, that we have converted into velocity profiles in meter per second, and we have written a small UDF that we have prescribed. Then at outlet, it should be physiologic. Outlet, there is a time varying pressure boundary condition, velocity inlet and pressure outlet. Then the velocity profiles, how the velocity profile changes when I am increasing the aspect ratio from 0.5 to I am going to 1.5, and I can say that the velocity at the neck is very high in case of high aspect ratio case. We can see impingement velocity is very high on the neck. Second observation is that when we are having multiple lobes in this aneurysm, there are two lobes, primary and secondary. Secondary lobe, there is very low velocity profile or recirculations are very high. That I will explain in later how it affects to aneurysm. This is the typical direction of flow. We can say in smaller aneurysm, the flow comes and goes into the particular outlets. But in B case, multi-lobed, we can see that this cross-mixing of the stream happens at the middle of aneurysm. What happens when there is a cross-mixing in the aneurysm, that I will explain in next slide. But just remember that multi-lobe aneurysm are very complex flow because of this cross-mixing. When I'm increasing again the size of the aneurysm, the velocity at the neck is increasing, but flow patterns in the aneurysm is very, it comes, slides into the aneurysm and goes out. How it will affect, we can see in smaller case, we can see that two Dean vortices at the middle of aneurysm. But when I'm going for multi-lobed, there are two pair of Dean vortices, which means that multi-lobe aneurysm is having very complex flow. And it was proposed that whenever aneurysm is having complex flow, that is more prone to rupture, which means that even aneurysm is having size is small, but it is having multiple lobes. It is very dangerous. It may rupture. In this case, we can say even size is very large, but it is very uniform like balloon. So we can see only one helical motion we can see in this aneurysm. There is no very complex flow into the, even having bigger aneurysm, flow is very simple. What happens to time average wall shear stress when I am increasing this size? I can say when I am increasing the size, the maximum value is increasing, which means that if I am having high wall shear stress, it will, the chances of rupture are more. So which means that in larger aneurysm or larger aspect ratio, the chances of aneurysm rupture is more. Similar for relative residence time, as I discussed already, it is nothing but a time spent by fluid to that particular region. And that multi-lobe region, in streamlines, I have shown that secondary lobe is having very low flow fraction, which is recirculations are large. And that reflected into the stagnation, which means that large recirculation, which results into the stagnation. So till now I was discussing about the cerebral aneurysm, which means that hemorrhagic stroke. But from the next is the another stroke, acute ischemic stroke. And current treatment for acute ischemic stroke is the EVT, endovascular treatment. We put stent, we gather that blood clot and remove using this stent. But problem with the current the EVT is that after removing the stent, after removing the blood clot, a lot of patients are facing complications, and research in this field is very low. Very few publications you will find. Very few research groups are also working on this field, and I will be working on this area in the polymy for my postdoctoral studies. And in EVT treatment, we have four major components. One is our vessel, or arterial vessel. Second is the thrombus, which means that blood clot. Third is the device, which means that that stent, which we use for removing the blood clot. And next one is the flow parameters. So this is the vessel. We can see circle of Willis. Thrombus, or which we can say blood clot. Device, that is we can say stent. And these flow parameters, which means that we can do both studies, in silico, in vitro. In silico means computational studies. In vitro means we are just mimicking those vessels outside the in lab. Just this is the, for example, patient specific vessel, but which is in the developing lab, not in human body. That we call in vitro. In both way we can study. So these are the results from that group in which I am going to join. They are doing very fantastic job in stroke treatment, computational biomechanics lab. So these are the results from their recent paper. So what they do, they will just mimic this endovascular treatment virtually, and they call it as a virtual thrombectomy. Thrombectomy is treatment to remove the blood clot. So what is their flow chart? They take the images again that create that vessel geometry or model. then put the blood clot, and they got the blood clot parameters by studying it experimentally. They will do stress analysis, stress strain, and from that they will model the rheological model for this blood clot. So what they have done the whole that uh, treatment or surgery virtually using the computer simulations, and they found that first attempt they were not able to remove the blood clot, but in second attempt they were able to remove the clots. But why the CFD simulations are important? Because it is very important for surgeons. For example, this we can say that maximum principal stress. From simulations, we can find that at which location stress is maximum, which means that at that location it is very high chances to rupture the endothelial cells on that walls, and it will create complications. That can be studied, and it will be very useful to surgeons during surgeries. Such results. Then currently I'm working with TU Madrid on the hemodynamics in the heart. This is some extra I can say. Just few slides I will explain what we are doing currently. Human heart, we know right atrium, right ventricle, collection of blood, then left atrium, left ventricle, passing of blood to various body organs. So again, we use 3D slicer to create this model. This is the heart, patient-specific heart that we have created. Flow chart is similar, which I have shown earlier. Then we can see velocity streamlines in the heart. This is the left heart only. For simplicity, we have started with left heart. These are the inlets, and this is the aorta outlet. So we can see the velocity streamlines in a cardiac cycle at various locations. Peak systole, we can see high velocity. And when we are going to deceleration phase, diastole, recirculations are very high in diastolic phase. But what we are trying to do using these computer simulations, they are trying to create a algorithm to train the machine learning algorithm so that from the flow patterns we can differentiate between disease heart and healthy heart. That is our main objective in this work. So this is, I have done some preliminary simulations for heart walls. These are the streamlines, how the heart flow happens in a cardiac cycle. Then the Q parameter, Q criteria, which is nothing but the difference between the vorticity and stress tensor. Then third one is the vorticity, how the vortex formation happens in the heart. And last one is the wall shear stress. You can see this wall shear stress, how at which locations it is maximum or which location it is very low. That can be, we can get such insights using computer simulations. This was all about my research, or which I am planning to do in some near future. I would like to thank Shastra for this opportunity. I would like to acknowledge a few people those shaped my thinking. They have given a lot of opportunity to me work with them. First is the Raghvendra Gupta. He is my PhD thesis supervisor at IIT Guwahati. Then Dr. Jayanand Sudhir. He is a neurosurgeon at Sri Chitra. Then Professor Patnaik. Currently, we are working together on this cerebral aneurysm rupture mechanism. Professor Patnaik is a senior professor in applied mechanics, IIT Madras. Then Professor Jose and Dr. Julia, they are from computational biomechanics lab, Polimi, Italy. I will join them in January, and I will work with stroke treatment. Then Professor Soledad and Jesus, they are from TU Madrid. Next month, I am joining them, and I will work till January with them on heart wall mechanics. And this is typical. This is video I have taken from heart wall, that industry, how they are using this CFD simulations for directing the surgeries. Thank you so much. This is all from my side, and now I am ready to take any questions if you are having. Please be frank to ask.
Yeah, thank you.
Yes, thanks.
Sir, thank you so much for this inspiring talk on this auspicious day and for being here on a Sunday evening despite your busy schedule. Sir, on behalf of Students Chapter, we would like to express a token of gratitude with a memento, and the same will be couriered to you, sir.
Yeah, thank you. Yeah,
Okay, so we will take the
yeah, sure.
questions. Yeah, so this is Dr. Mahesh, a small memento from our side to you.
Yeah, thank you, sir. Thanks.
Thank you. Yeah, now you can as well read the questions directly from the chat, or do you want me to
No,
read?
I can read, sir. Okay, Akash, is
Yeah.
the recirculation not affected by the inlet pressure of blood? If so, is there any conclusion like people with bifurcation angle of X requires minimum blood pressure of Y to avoid abnormality? Because inlet pressure will not affect, because inlet boundary condition we are using patient specific, which is we have taken from TCD. So it will not affect because we are mimicking the inlet boundary condition. So I hope that I have cleared your doubt, but if you have further any questions, you can write to me. I think I have shared my email also. Then next question is, a lot of studies shown deal with wall surface or changes in cross section along the fluid flow. What is your comment on dynamic wall, where the internal wall dimension changes with flow, not rigid wall? Exactly right. If rigid wall and dynamic wall, there is a difference in wall shear stress values. If you are going to dynamic wall, your wall shear stress value will be lower because the pressure will dissolve by extending the elastic limit. It will store energy, and then again it will use for discharging or creating the uh, driving force. So going to flexible walls is better, but for starting purpose, anyone can start with rigid walls. But in my case, our objective was to deal with geometric variation, but yes, definitely it will change, and it's always better to go for flexible walls. What about the sleep condition at all? Is that no sleep for blood flow in such capillaries? No, actually, we are not dealing with capillaries because this vessel is almost 6 mm carotid artery, and even in circle of Willis, minimum will be 2 mm. And capillaries is something different than the these vessels, because these are the large vessels, and we can use no sleep boundary condition. Then Rajshri, oh, thank you for the information. We performed simulations with symmetric geometry with Newtonian fluid, ventilator splitter with air, and found that there is a maldistribution of flow even when the geometry is symmetric. Please let us know if any flow maldistribution was observed in the simulation done for Newtonian and non-Newtonian fluids in your study. I am not able to understand the maldistribution meaning. Can you just switch on your mic and clarify on that?
Hello, sir. Am I
Yes,
audible?
yes, yes, yes.
So, good evening, sir. So, the ball distribution, I means the difference in the total mass flow rate between the two split arms.
Okay.
So, that is a mall distribution, I
Okay,
mean.
that is not equal, you are saying.
Yes,
In
sir. In our simulation that we have
okay.
performed,
Mhm.
flow distribution was not equal.
Okay, that depends upon your size is equal. Daughter vessel that when it distributing, the daughter vessel size is equal. Still, it is showing difference in mass flow rate, right? Am I right?
Yes, sir.
Okay. I
Yes.
think I have to see the geometry actually. I cannot say anything without seeing any result or geometry. But if you want to explain me that, you can just share that geometry with me. Then I can comment on that. So by just question, it is very difficult for me to explain anything.
No, her question, if I can just add on, Dr. Mahesh, like what she is saying is, even if the geometry is symmetric,
Okay.
the distribution may not be symmetric. I mean, the flow will not be getting equally bifurcated when it flow through splits.
Yes, yes. But if yes, if
So in this case also, that should be the case, right? Because here the angle itself is tilting towards, and it is clearly seen that in one channel the more blood goes than in another
yes,
channel.
Okay.
So she was asking the repercussions, consequences of such.
Actually, yes. If the daughter vessels are equal size, it should not be. It should not happen like this, because according to flow physics, it should be equal distribution. If angle is same, even daughter vessel size is same, it should have same mass flow rate. But again, if you have some region which is having very complex flow at bifurcation, such as dilation at bifurcation itself, then it may change the distribution.
Fine.
Yes, sir. Fine,
Yeah.
sir. Thank you, sir.
Then carotid artery to the brain, understand that angle of bifurcation is important to have equal distribution of blood. Okay, same question, right? Okay.
Yeah.
Okay.
No, do they? The question means, do they really want same distribution of blood across?
No. In carotid, it should not like that. In carotid, there is a distribution of 70-30. 70% of blood mass flow rate goes to internal carotid artery, which goes to brain, and external should have 30%, which goes to face. That is very standard value. That's why people use register into the experimental setup to tune such flow distribution. The next question is Ithasai, currently final year students. Sir, firstly, thank you for insightful. Sir, in few cases, arriving at the physical interpretation of the simulation result is difficult. Could you please share some experience in understanding the physics behind the result? Or if you are, I'm not able to understand what exactly you want to ask, can you just switch on the mic and if you want flow physics or something else?
Sir, am I audible, sir?
Yeah, yes.
Good evening, sir. Sir, actually, when we perform simulation in some reactors which have multi-phase characteristics, to arrive at a particular understanding on the result we got, it would
Yes.
be difficult in few cases. So,
Okay.
how could you please give some advices? So,
Yes.
regarding
But whenever you are picking some research problem, each problem has some very well-known articles, highly cited and very good journal articles. Pick those first. Do some validation with those. It will give some confidence that yes, my results are good, because it is comparable with those results. And then you can play with geometry or your flow conditions, and from that base you can explain your physics. But yes, you have to go to some standard literature to understand the physics, how I should describe it, or how to understand it. That is how I follow.
Thank you, sir.
Then next question is different mode. How challenging is it for a chemical engineer to take up problem in medical field and solve it? Actually, it's not like that. We are a chemical engineer and we cannot do simulation in medical field. I even at the beginning of talk, I discussed that our core subject are mass transport, fluid mechanics, and transport phenomena, and that is what we do in medical field simulations. It's not about branch actually. It's about interdisciplinary approaches. When you go to medical field, it comes with various branches, not only chemical engineering. But just you should have some knowledge about physiology, and you can do that. It's not a very, I think, tough task. Yes, it is very relatable to chemical engineering because our common courses are similar. Then Venkat Sharma, 2020 batch. Sir, all humans will have unique neutral schema like different artery vein thickness, shapes, etc. Sir, in your your point of view, how difficult is it to model such scenarios in CFD? Wouldn't it require immense analysis before modeling? Yes, there are a lot of studies which have given the thickness of various vessels, and from that you can get. But if you are going for patient specific thickness, yes, it is a challenging task. It is very difficult to get each patient's arterial thickness data. But standard data is available. That, for example, if you are having carotid artery, it will having that much thickness range. If you are going to circle of Willis, that is having particular thickness range. That is well reported, I think. And challenging in CFD, CFD you can give, because when you are giving the solid wall. While pulling, you can give the thickness. It is very easy to give thickness for FSI simulations that you can give very easily. Just you should have the data of that arterial wall thickness.
Thank you very much, sir.
Yeah, thanks. Then Akash, thank you for your previous answer. I have another question. Could you please share your experience on immense level of data from all the simulations? Following the previous question, how many rough iterations you have to perform for the convergence, and does the number of cells in CFD software had a vital impact on your result? Yes. For the beginning, you have to struggle a lot for convergence. Once you get confidence, for example, for me, now I have almost done simulating this kind of results for 5-6 years. So I don't face such complications. But yes, beginning you will face, but with time you will learn. It's kind of skill, and you will improve with time. So number of cells, yes, it will change your results. That's why we do mesh independent study. In each CFD study, whenever you submit article, a reviewer will ask your mesh independence results, and that is required, because with change in number of cells, there is a slight change in your results. So our mesh should be fully resolved, and for that we do mesh independent study. Then there are no further questions. Okay. Srinivasa, I'm currently working on analysis of airflow through the ventilator splitter. As every patient has a specific requirement for inflow from it, apart from changing the splitter angle. Is there any way to change or control the inflow from the splitter? Frankly speaking, I don't have any idea about ventilator and the splitter, but if you want me to explore, then I have to go for some research paper, and then I will get back to you on this. Thanks. I think if you have further questions, you can ask.
Okay, I think this is a very charging weekend. Right, good. Yeah, you can go with the schedule. Who is on the...
Yes, sir.
Yeah.
Thank you, sir. Now we are at the end of our event. Now I call upon Mr. Gautam Kumar, Secretary of our Students Chapter, to propose the vote of thanks. Please take over.
Thank you, Harshit. Good evening to one and all present here. I, Gautam Kumar V, consider the occasion as an honor and privilege to propose the vote of thanks. It is said that feeling thankfulness and not expressing it is like wrapping a present and not giving it. Today, I take this opportunity to put all my gratitude into words. On behalf of IIChESChap Student Chapter, I would like to take this opportunity to thank everyone who has made this event possible in such a great fashion. I would like to extend our warmest gratitude to our guest, Dr. Mahesh Nagargoje, for taking his precious time out and consenting to give a talk. Sir, indeed, your words have inspired the students. I would also like to thank our student coordinator, Dr. P.R. Naren, and all the alumni members for their contribution and support offered. Last but not the least, I'd like to extend my warmest thanks to my peer fellow mates who have helped in organizing, participating, and thus making this occasion a grand success. Once again, thank you everyone.
Thank you, Gautam. We have come to the end of this event. I thank one and all for making this event a success. Thank you. Now the recording will be stopped.